Steve. I work in South Portland at Fairchild Semiconductor, and we make wafers like this, which have products that go into little black boxes there, and that's a board from a cell phone. That's a Motorola cell phone. I think it's about 3 or maybe 5 years old, so it's a little outdated, but and we tend to make the smaller ones in that. So how I got involved in this is I grew up during the 60s, so I was very interested as a young kid in the whole space race. And my dad's an engineer as well, so I was very interested in math and science. And so
in Maine?
No, I grew up in Connecticut. So,
Connecticut,
yeah,
awesome.
near New London, actually.
And you have connections there? Or
yeah, I grew up in Connecticut. That's where my brother's from. I grew up in Naugatuck, and live in Milford in the summer a little bit.
Well, my dad designed sonar, so he worked over in New London at Underwater Systems Center there. Yeah, and of course during the Reagan era, it was huge. I mean, Groton was just booming. I mean, they were building Tridents, 1 or 2 every year. So. Anyway, I was real interested in math, science. I always liked it, and so I ended up going and studying engineering in college. And I got interested in semiconductors because out of all of electrical engineering, what I liked about semiconductors is you could actually look through the microscope and actually see it, as opposed to like designing a circuit where you might run a simulation and you just see a waveform, or you tune a waveform onto an oscilloscope. I found that a little bit a little nebulous, that you're just looking at a waveform on an oscilloscope. I kind of like things, I grew up, I built a lot of model airplanes when I was growing up and did a lot of woodworking, so I kind of like building things. So that's sort of what I liked about semiconductors. Maybe in retrospect I should have been a mechanical engineer instead of an electrical engineer, but I liked the fact that you could actually see it. I mean, I always kind of like gears as well, gears and engines and stuff like that. So, it's a fun thing to do. I mean, we make these wafers. It's pretty unusual because, like a lot of other things, domestic manufacturing is getting to be less and less in semiconductors. We've managed to continue to be relevant because we make non-generic products. So we make products that are a little bit more niche-ish, primarily in the areas of managing power. We make things like on this, we make things that go between the battery and the other chips that regulate the power. And then the other thing we make is, this is from a flip phone, so there was a ribbon connector here. We make also interfaces to the ribbon connector that allows you to send data across the clamshell very quickly. So,
Well, there's a piece that you missed here, which is, how did you change from being interested in the space race, NASA, all of that, to doing
one of the things I always understood, I like the astronauts and all, but I always was a little bit different than most people in that I kind of realized that it was really more of an engineering accomplishment than, like a heroic thing. I mean, the astronaut was just a guy who was in the ship, but there was tons and tons of other people. So when I followed the space race, I was maybe different than most kids because I would try to read, I would actually go and read the mission reports, and I would read, I would read the stuff that like Wernher von Braun would write about the rocket performance. So to me, I was just as interested in the engineers. And one of the things that, of course, the space race really pushed semiconductors. If you look at, the sales of semiconductors primarily in the 60s was for missiles and rockets. So all the improvements were really pushed by the space race, and I found that really interesting. So the electronics of the space race was something that I found really interesting. So, I always thought it was a little strange that it got spun as such a sort of personal thing with the astronauts doing everything, whereas there was, 100,000 engineers designed the Saturn V rocket, and all of those people worked just as hard as the astronauts. So. That's kind of why I wanted to go into engineering. I wanted to work on things like that. And, I've designed chips. I've designed transistors that are now on Mars because we had some parts on the rover. I've designed chips that are circling Saturn now because we have chips on the Cassini space probe, I believe. That we have chips on Voyager, so we have chips that we made in South Portland that aren't even in the solar system anymore. Every shuttle launch, I always cringe because we have chips on the shuttle, and I just hope that they all work right. So it's, virtually every computer that anyone has, there's something that was made in South Portland in it and I might have designed the transistors in it. Because of the manufacturing capability, the leverage of an individual person is tremendous. I mean, there only has to be a few people in the world who know how to do transistor design, and everyone can get transistors because we can make them. We can make so many of them. So
when you work, do you work mostly individually? Is there a team that works with you on the design?
It's a big team. No one can do anything. It's like rollerball. It shows the futility of individual effort. Right? It's just like there's almost nothing. I mean, you can do things in your little area, and there's plenty to do. But I mean, I don't even touch the wafers. I never touch the wafer. This is actually
the most you've touched one.
This is the most I've touched one in years. I mean, I go on. Well, I'll go in the lab and probe them, but when they're being made, I never do anything. I don't even go in the place they make them. I mean, it's right down the hall for me, but I don't actually go there. There are other people, because each machine, I mean, has just like the photo tools that put the images on. There's probably 25 equipment guys and maybe 25 process guys that just support those machines. So these guys, and then there's etch machines and metal deposition machines and implantation machines, and each one of those has a group of 50 people that just make those machines run, because it's so difficult. I mean, the power has to be so perfect, the input chemicals have to be so perfect, the control of the machine has to be so perfect. The ability to align one layer to another. We can align one layer to another to like 0.1 micron, and human hair is 100 microns. So we have the ability to put two layers no more than 0.1 microns off from each other than what we want. So all of that stuff takes a lot of people, and there's some people who all they do is work on just making sure that photo tool aligns to the previous layer rate. So we have about 800 engineers that make this, and all 800 of them have something to do with this. So it's a kind of the ultimate team.
How many layers are there on one?
This one here this would be in the neighborhood of 25 layers.
25 layers. Wow.
And it takes about, this will take about 50 days to make. And it costs us about $300 to make it. And
material-wise,
total cost, fixed and variable cost. So the whole cost, our costs,
including all the salaries and all the
labor, including overhead.
Okay, because you make a bulk once you get it going.
Right. Our true cost of goods sold on this is about $300, but that doesn't include R&D. So it's for the gross margin calculation, this would be $300. For the operating margin, it might be more like $400 to the overhead in.
How have the requirements of your job changed over the last 10 years, if at all? Do you need to know more than you? Is the technology changing? You have to...
The physics haven't changed at all. Right. The tools are obviously better but more complicated. The process flows tend to have more layers. I mean, when I started, process flows, we were about at 1 or 2 microns, and a process typically had about 14 layers. The process I work on now are at 0.35 microns, and they have about 25 layers. So the complexity has gone up quite a bit. The materials have changed a little bit. The tools have changed a lot, obviously much more complex.
So do you do constant staff development to learn the new tools, or how does that work in that?
Typically we'll interact with the vendors, and we'll also read all the technical journals, we'll go to trade shows. So it's constant, always improvement. I mean, we go to conferences and they talk about the 10-year roadmap, so we're already sort of getting an idea where we're going to be in 10 years and what tools will be needed.
Oh, wow.
There's a whole...
It's like we do in education.
Yeah, there's a whole trade group that all works on is the roadmap, because the equipment we're going to be using 10 years from now is being designed right now.
Sure.
And the products we're going to make 10 years ago are being conceptualized right now. So there's a lot of people who work on the leading edge.
Are those U.S. vendors that are making that equipment? Or is it...
Some are. We buy our photo tools from ASML, which is from Holland. We buy our etch tools from Lam, Applied, they're American companies, or
okay, we're going to do one more shift,
Japanese
counterclockwise.
company. Yeah,
Thank
so
you. This will be our last shift.
all over.